sorry about that, actually the recording just stopped. Alright, sorry about it, there was some issue with the recording. Right, okay, I guess I have 30 minutes of recording. Right, okay, we are already 30 minutes done. Alright, sorry about that. Okay, so yes, let's go with continue with problem number 2. So what we have, okay, for a simple, okay, so first for a simple cubic Bravais lattice, all the points on the corners have the same environment. Okay, so this is the thing about a Bravais lattice. All the points on the Bravais Bravais lattice, that way they will have the same environment. Okay, so here let me just draw it for you. Let's say we have this. Okay, let's say let me just draw. Okay, let's say we have this simple cubic. Sorry. Okay, let's say, let me just show these points with a red color. Okay, so these are our corner points for a simple cubic. Okay, it is not exactly cubic, but this is, I hope you can understand this cubic. Okay, so let me just check there was some issue with the recording. Alright, so this is a simple cubic, and as you can see, the simple cubic, they have the same environment. Okay, so for example, if you see this cubic, okay, now you will say, okay, it has two neighbors here, but if you do if you draw the, because this is just because in a solid, if you make a solid of it, so there will be periodic boundary, so you will just you will have another cube here because of the periodic boundary condition. Alright, so alright, so you will have one here as well, and you will have I can't draw this here, but you can imagine like there will be one more cube in this direction as well, and on the top as well. Okay, so on the top as well you will have another cube, and similarly you will have behind as well, there will be going to be a cube. Alright, which you can just close. Alright, so because of this, you can see that for each of these point, they will have the similar environment. Okay, so like for each of them, there will be 6 nearest neighbor. Okay, for this red point, there is 1 is here, like 2 is here, like 3 is here, and if you do the periodic boundary cursor, then there will be 1 on, as we have discussed earlier. So like if from here to here there is a Bravais point, then there will be a -1 as well. You can see there will be a -1. Similarly, there will be a -2, and there will be a -3 as well. Alright, and if we extend it, then we can see those -1, -2, -3 as well, and that will be the same for each of these points. Okay, so here you can see that for a simple cubic, all these points on this cubic Bravais lattice, they are same, and that is why this is a Bravais lattice. Okay, so all the lattice points on a Bravais lattice, they have the same environment. They have the same, means they have the same environment. Right, so now we have and okay, and then now in all the three parts of the problem, okay, so in this problem, what we have to find whether the structure that we are now forming from this cubic lattice, they are Bravais lattice or not, and if it is, then we have to give the primitive vectors, and if it's not, then we have to describe it as a Bravais lattice with as small as possible bases. Alright, so now in all the three parts of the problem, we have a simple cubic structure with additional points So we need to compare the corner points with the new points. Alright, so just a brief, let me just give a brief on this. Okay, I have done it with proof. Alright, I guess fine. Okay, now just a brief note on the primitive vector. What is a primitive unit cell? Okay, so what is a primitive unit cell? Volume of space or maybe okay, now a volume of space that when translated through all vectors in a Bravais lattice. I'm not sure if this in Bravais lattice. So this is just for your information. I guess for this problem this is not, but I included it just for your information. Just fills all of space without either overlapping itself or leaving voids. This is what I am giving this intro because as has been seen, if the system is not going to be Bravais, we will try to find a primitive unit cell which will help us to make that structure. Okay, so either it will be a Bravais lattice, and within the, if it is a Bravais lattice, then we can see the primitive unit cell in that also, and even if it is a Bravais lattice, then we have to define a primitive, we have to look at the primitive unit cell and get the primitive lattice vectors. Okay, else we have to find this primitive unit cell for the structure. Now there is then another thing we have to remember, there is no unique way of choosing a primitive unit cell of the lattice. Okay, so this I am writing because when we will what we will see is that for a Bravais lattice, if you define some primitive lattice vector, then there could be there is not a unique primitive lattice vector. You can have more than one type of one set of primitive lattice vector. Alright, so this we also need to keep in mind. Then one thing again, a primitive unit cell must contain precisely one lattice point. Okay, so here you can see that basically you can see that number of lattice points per unit cell. If we check for this simple cubic, then it will be 6 divided by 6, that will be equals to 1. Okay, so each of this corner points, so we just have the lattice point on the corner, and each of them will be shared by, if you just imagine like we have one cube and we will have one in this direction as I drawn earlier, one in the left side, one in the right side, one in the top and the bottom, and then front and left as well. So each of these corner point will be surrounded by 6 points, so each of these corner point will be shared by 6 cubes. So this you have to imagine, and thus the total number of points within a unit cell will be, say, total 6 points divided by each of them is being shared by 6, so we are getting just 1/6 of each lattice point in the unit cell, and the total number of lattice point in the unit cell per unit, this primitive unit cell, this unit cell is 1, so this is a primitive unit cell. And the primitive lattice vector for the simple cubic, lattice vectors for the simple cubic here will be E1 vector will be given by A times of x cap, E2 vector A times of y cap, and E3 vector A times of z cap. So I am just taking this primitive lattice vector for now, where this A is this length of this cube. Okay, now we will go back to our problem. So in our problem, what we are seeing is that we have this different kind of structure, and we are making it from this cube itself. Okay, we have a simple cube of length A, and from there we are going to make all these kind of structures. Okay, now first structure that we have is a base centered cubic. Okay, so we have a base centered cubic. So what is a base centered cubic? So in a base centered cubic, again I will draw this simple cubic. Alright, so this is our simple cubic, and so these are our corner points of the simple cubic. And now what we are seeing is that we are making a base centered cubic from this. So for this, what we will do is we will put 2 points on the center of this. So like 1 point here, and let's say I guess on the center of this face. This is how I find the center, like the 2 diagonals will meet at. So this is how it is defined. Base centered cubic is defined. It is a simple cubic with additional points on the centers of the horizontal face of the cubic cell. Okay, so we are going with the horizontal face of the cubic cell are these 2, and there will be 2 points here. So we have basically 2 additional points. So what we can see here, so let me just write it first. New points have same environment as the corner points. Alright, so here you can see that this green point, they are going to have the same environment. So for example, like if you take this, so if I extend it, okay, if you extend the cube, so what will happen, you will have 1 point here as well. Okay, you will have 1 point here, 1 point here, and 1 point here, just like this green one. Okay, so this green one also has this 4 points, and it has 1 green point just at the bottom, and will have a 1 green point just at the above, and the 4 red points on the square. So I have drawn this as red and green, but in reality they are just lattice points, just to distinguish them. Now if you go to this red points, if you go to any of the red point, to the one that I have drawn to this one, alright. So you can see that if I extend this cube, if I do make the complete lattice, then what will happen, each of these red point will be surrounded by 4 green points, and on the top there will be a red point, and on the bottom there will be a red point. So similarly is the case for these green point, and similar environment we have for the red points as well still. So this whole structure is a Bravais lattice, because all the points they have the same environment. Okay, so we just need to compare the case with this corner, because we already know that the corner point they have the same environment, and now we just have to check that these new points they have the same by adding the new points, is the environment between this red point and the green point they are the same or not. So for the green points also there will be 4 red points in the square, and 1 green point on the top and 1 green point on the bottom. And similarly for the red points there will be 4 green points at a distance of, you can see this will be a distance of A, a by root 2. Okay, this distance, this will be a by root 2. So at this distance there will be 4 green points for this red one, similar to like at similar distance for green one there are 4 red points, and at a distance of this a, each red point already has one red point, and similarly for green point also there will be at a distance of this a itself there will be another green point. Okay, because this distance between these 2 green points, that is also, as you can see in the diagram, that is also a. Okay, now we will just write it down in words. So these points are always surrounded by, okay, or green and red points are surrounded by, or maybe just like odd points, because I have mentioned in them as green and red, but actually they are the same. They have the same environment and they are a part of the lattice. So odd points are always surrounded by 4 atoms in a square in the horizontal plane and 2 atoms in the vertical direction. So it is a Bravais lattice. Alright, and now if we talk about the primitive lattice vector, so primitive lattice vectors, so they are given by a1 vector is equals to a by 2 x cap plus y cap, a2 vector equals to a by 2 x cap minus y cap, and a3 vector equals to a times z cap, or they could be defined as a1 vector equals to a times x cap, a2 vector equals to a by 2 times x cap plus y cap, and a3 vector equals to a times z cap. Alright, and this you can check, okay, for basically how they are primitive lattice vectors. So I will just show this for this. So let's say I start with this point, that this is my origin O, and then I have this a1 vector which is a by 2 x cap plus y cap. Okay, so let's say this is the x direction, this is the y direction, and then let's say this is the z direction. Okay, alright. So what I will have, I have a by 2 of x cap plus y cap. So I will go a by 2 of x cap, or let's say okay, so if I go to a by 2 x cap in this direction and a by 2 y cap in this direction, okay, so that will be a vector this. So a1 vector will be this, and here if we do a periodic boundary condition, there will be a green point. Okay, if we extend this cube, there will be a green point. But I can't draw it here. Maybe let me just move all of these. Okay, so if I just move everything down. Okay, so just to show you, so let's say I extend it here. Let me draw the extended with the black only, or maybe with the blue. Yeah, blue would be okay. So this is my extended cube. Okay, so I can extend my cube here. I can extend my cube here. Alright. So if I extend my cube like this, okay, so then again I will have one green point here. Alright, and I will have a green point here on the top as well. Okay, and then there will be these red points as well. Let me just draw this green points with some, like there will be some green point here, there will be some green point here, and there will be red point here, corner, which will be the corner point. There will be a red point here as well. Alright. So if you do your A1 vector, which is given by a by 2 x cap plus y cap, so this will be your A1 vector. Okay, then similarly you have a by 2 x cap minus y cap. So x cap and minus of y cap will give you this. This will be your A2 vector, and okay, along A2 vector again you will have this, and A3 vector again we will get you will get a this lattice vector direction. Okay, and then so basically this by using this 3 primitive lattice vector you can mainly make your whole lattice. Okay, you take an origin, you start drawing this A1, A2, A3, you will get this Bravais lattice point. Okay, sorry, okay, this is the black line, and this is the your vector E3 vector. Alright, so with this A1, A2, A3, you can make your whole lattice. Okay, and similarly we can have this a times of xl, so you can check that if you have if you instead of this you can take a times of xl, then you will go to a red, from a red point you will go to a red point. A by 2 x cap plus I cap will give you a green point, and then A3 vector az cap will again give you a red point. Alright, and you will see that even that will also form your lattice if you just go with that. Alright, so this I will leave for you to check. Alright, now let's go to the B part. The B part is just a minute. Hello, sorry about that. The recording is okay. Alright, let's go to the next part. So the B part is our side-centered cubic. Side-centered cubic. So how is our side-centered cubic? So let's say I have this cube again. Okay, let me just draw the cube again. Right, and here we are going. These are our corner points. Now for side-centered cubic point, what is given in the question is that a side-centered cubic, okay, so let me just make it a green. It's a simple cubic with additional points in the centers of the vertical face. Okay, so how it is saying that draw it on the vertical faces, or the centers of the vertical faces. Alright, so let me just draw these centers. I guess so they're not going to be exactly centers, so we will have. Let me just draw these lines. Let me just make an approximate. Sorry, what is approximately this will be somewhere here. This will be somewhere here, and then on the center. Okay, yeah, there will be 4. Okay, so there will 4 vertical faces, and then we will have this 4 new ones. Okay, so here let me just draw. Okay, so let me just draw this now. Okay, so let me just show you. Okay, so this one is on this face, and similarly that one is on the front face. So these 3-dimensional figures are quite difficult on a 2D surface. Okay, so basically this is the side-centered cubic now we have. Now what we can see from here is, we can see that new points have different environment as compared to the corner points. Alright, so why we are seeing here they have a different environment. So here you can see that this okay, so for each of these green points, okay, there will be 4 red points which will be the nearest neighbor, and there will be these 4 green points. If you extend the cube again, so I'm not drawing it again because we have quite less time, so you can try to draw it and imagine, but as I have shown you here, okay, you can just extend the cube like this and draw and maybe draw and imagine stuff. Imagine this structure if you, in the periodic case. So by this you can check that for the green point there will be 4 nearest neighbor red points, and then on the horizontal plane you will have 4 nearest neighbor green points as well. So in total there will be 8 nearest point. And similarly for this this one as well, there will be 4 of these green points. Okay, there will be 4 green points and 4 red points. Okay, and each of them will form a tetragonal block, but what will happen is that the direction will be a little different, so it will be a rotated one. Okay, so the tetragon that you will form from the nearest neighbors of a green point, okay, tetragonal structure that you form, it will be tilted compared to the tetragonal structure that you will form from the nearest neighbors of these red points. Alright, so there is a difference, so the environment is not the same for each of them. So for this is a little tricky, so I will encourage you to maybe draw the structure and draw it further, and if you have any doubt then I will try to include this drawing of this structure in the next session, but right now I am just gonna write what I just said, right? Okay, so the nearest neighbors of corner points are the new point. For the corner points, let me suppose these are red, are the new points which are the green one. Now each corner point has 8 nearest neighbors, and they form a okay, so for each corner point there will be 8 nearest neighbor green points. Okay, so only the green points are there, so that you can see, like if I draw a small block, I should have drawn, okay, right, if I draw this small, okay, so there is one corner point here, then there will be one green point here. Okay, let's say this is my corner point. What I'm saying is that let's say this is my corner point, and let me just extend it here. Okay, sorry, I guess I said something wrong during that. I said right about the green point, but I guess I said something wrong about the red points. So I will not draw a cube, but basically you can extend this cube. Now we will have one green point here, one green point I will have here as well, which is there. Then similarly there will be some cube in this direction as well, so that will have some face and everything. So on this face also I will have one green point. Alright, so one green point here, and here again I will have one more green point. Alright, and then there will be these 4, and then again there will be some face on the top as well of this red point, so there will be 2 points here as well, and then okay, for this face, and then there will be 2 points in this direction as well, okay, just on top of these points. Okay, so in total there will be 8 points. So this is a very rough diagram. You can try to imagine. Hopefully, I guess you will be able. So basically, similarly, you can think that okay, if we just go with this 4 point, then on top of each of these green points, there will be some other green point on this plane, and on this other plane. Okay, so there will be extension like this, and then there will be extension like this. So this is a very cumbersome process, but there will be some green points here. Okay, so there will be total 8 points, which will be this new points. For this green point, all the nearest neighbor will be the green points only, and that will not be the same from your green point of view. So that makes it okay. So like for this system which has the Bravais lattice, we see that either there will be 4 red points. For green point, there will be 4 red points in the plane, and there will be 2 green points in the vertical direction. And for each of the red points, there are 4 green points. Okay, for new points that will on the horizontal plane, and then 2 red points in the vertical direction. While in this case, for the red points, the nearest neighbor, they are only going to be green, while for the green points, there will be nearest neighbor, both red and green will be there, are going to be the nearest neighbors. Alright. So each corner point has 8 nearest neighbors, and they form a tetragonal block, and that's why the tetragonal block that these two nearest neighbors of red and green will form, they will be rotated, and they form a tetragonal block. The new points, green one, which corner point is the red one. The new points, green one, also have 8 nearest neighbors, 4 corner points, which are red, and 4 new points, which are green. But they form a tetragonal block that is rotated from the other one. So there is a difference in direction. Alright, so you can draw the nearest neighbors for green one as well, and then what you find that there will be 4 red points, and the 4 green points will be the nearest ones. Alright, so I am not drawing it for now because we are already getting out of the time. So it is not a Bravais lattice. So it is not a Bravais lattice. Okay, this one is not a Bravais lattice. Then so now we will find the perimeter centimeter. Now what we can see that this structure, now this is not a Bravais lattice, so now we have to find some Bravais lattice which can with the smallest basically we need to find now a new perimeter unit cell of Bravais lattice, in which this could be from which this structure could be made. Now this structure can be described by a single by a simple cubic Bravais lattice with a 3-point basis. The 3-point basis will be d1 vector equals to 0, d2 vector is equals to a by 2 x cap plus y cap. Okay, so the question was this only. If we can, then we have to find the where the it is, and if it is not, it is a Bravais with as small as a basis. So as you know, a crystal structure is formed by a lattice and a basis. So if the lattice that we are talking about, it is not a Bravais lattice, then it is a, then whatever this crystal structure is, then we have to describe it as a Bravais lattice with as small as possible basis. So what we are saying is that this structure, it could be defined as a simple cubic Bravais lattice with this 3-point basis, which is d1 equals to 0, d2 vector a by 2 x cap plus 5 x cap plus z cap, and d3 vector equals to a by 2 y cap plus z cap. Okay, so what we are saying is that the primitive lattice vector for this system. So we are saying the primitive lattice vector are just a1 is equals to ax cap, a2 is equals to ay cap, and a3 is equals to az cap only. Okay, while we are taking this we are taking a basis on each of these certain. So let's say each of these red points, it will have a basis, and this basis given by first one, it will be on this on the 0 center. So one basis will be this this on the 0 itself. So what a basis is, so this will be one atom. Then we are saying that there will be one atom on the 8 by 2 x cap plus z cap, one atom or whatever the point is, a by 2 x cap plus z cap and y cap plus z cap. Okay, so you can take y cap or you can take minus y cap. So basically you can see that this point, so let me just draw it with a blue one. So I will take like this is my d2 vector, what I am saying, and this is actually a minus of d3 vector, but let's say this kind of thing. So these 3 points, point 1, point 2, point 3, this will be our basis. So as you can see, so this is your base. So what you will do, you will form a simple cube, and at each of the simple cube you will put this thing as a basis. You will put one atom at the point, and then you will put one atom at this position of point atom 2, and one point. So I have taken y cap in this direction, although okay, so you can check. Okay, maybe it will come in that other direction, but I guess that is pretty much clear. So with this thing, you basically taking this. Okay, so at each of this simple cubic, now we will not have just one red point. We will have one red point and these 2 green points. And if we just put it on each of these corners, then what you will see is that you have recreated this structure. So this structure could be made by a simple cubic lattice with this as the basis. Okay, here I have drawn this thing. So this is actually minus d3 vector. Okay, so this will be a by 2 y cap plus z cap. So y cap is in this direction, so d3 actually will come in. Okay, d2 is in this way and d3 will come in this way actually, because if you have x cap, y cap and z cap is in the perpendicular direction. Alright, and there also by periodicity there will be a green point. So if I just take these 3 points, okay, this will be my point number 3, then I can make the whole system. Alright, so I guess this is clear. Okay, you can also check that if you go to next green point, so next one will have this green point and the this side of green point, and we can make the whole lattice. Alright, so hopefully this is clear. Right, so this will be our basis. So at each point we have to take one red point and this kind of 2 green points, and this is our d2 vector. This is my d3 vector. So this is my d3, this is my d2, and d1 vector is just a 0 vector. Alright, let's go to the last part, which is C. This is our edge-centered cubic system. Now what is an edge-centered? So edge-center is, okay, again I will have my simple cubic structure. So these are my corner points. Okay, this is my simple cubic. Alright, now for the edge center, my new points, these are on the center of this edge, so you can look at the problem. Okay, the edge center cubic is cubic center with additional point at the midpoints of the lines joining the nearest neighbors. So these are the nearest so these are here will be our new points. Alright, so here we can you can automatically see that this is again not a Bravais lattice, because the number of nearest neighbor will be different. So the corner point are going to have the 6 nearest neighbors. So this I leave a task for you. You can check that. So the nearest neighbor for a corner point will be 6, while nearest neighbors for these new points will only be 2, which will be these 2 red points. So that's why this is the red and green points. They are not going to have the same environment. Okay, the red points will have the same environment as compared to all the red points, and all the green points will have, but the red points and green points will not have the same environment, and thus it is not a Bravais lattice. Okay, I guess hopefully now these points are clear. So let me just write it. Now new points have different environment as compared to new points. Okay, let me just mention that new points are the green ones, have different environment as compared to the corner points, which are the red ones. Alright, so let me just show why. Corner points, red ones, have 6 nearest neighbors, but the new points, which are the green ones, only have 2. Okay, so it is not a Bravais lattice. And now we for this system as well. Now this structure can be described by a simple cubic Bravais lattice of side A. Okay, of side A. Okay, I didn't write of side A, but that is I guess obvious. So that is not included. That is, let's say, limit of side A with 4 point. Okay, let let me also write here as well with the 3 cubic vertices of side A with 4-point basis. Okay, so d1 vector will be equals to 0, d2 vector will be equals to a by 2 x cap, d3 vector will be equals to a by 2 y cap, and d4 vector will be equals to a by 2 c cap. So here you can see that basically what you have to do, you have to take this basis. If I extend it here, okay, this will be my x, y, and I'm taking this as z. So if I extend it here, so let's say I have extended this cube here. Alright, so there will be 4-point basis, okay, and there will be a green point here as well. So d1 vector 0 will correspond to this red point, d2 a by 2 x cap. So this will be my d2 vector a by 2 x cap, then a by 2 y cap. This is my d3 vector and this is my d4 vector. Alright, so this will form a basis. So first of all, to make this structure, but this head-centered cubic, what I will do, I will make this cube which is just by these red points. Then for each of the red points, I will take these 3 more points as well. So this 4-point basis is what I will make, and you can see that if you just repeat it for each of the red points, then you will get this structure. Alright, so let's discuss the structure. Okay, now let's just go to problem number 3. It's already 8:24. Alright, so in problem number 3, is taken again from Ashcroft Mermin. It is problem 1 from chapter number 5. Okay, so what we have to do here is we have to prove that a reciprocal lattice primitive vectors defined in 5.3, which is, we know what have given. I will just give you the equations again. So what we have to basically prove that this b1 vector, b2 vector, b3 vector, which are the reciprocal lattice primitive vectors, they satisfy this condition. Okay, and they have also given a hint as well for us to solve. Okay, let us solve the part A then. So for part A, what we have is, first we have b1 vector is equals to 2 pi times e2 vector cross e3 vector divided by e1 vector dot e2 vector cross e3 vector. Alright, then we have b2 vector is equals to 2 pi times e3 vector cross e1 vector divided by e1 vector dot e2 vector cross e3 vector, and I have a p3 vector is equals to 2 pi times e1 vector cross e2 vector divided by e1 vector dot e2 vector cross e3 vector. Okay, so this is the formulas that we all know, and also we should remember this ai vector dot bj vector, that is equals to 2 pi times, yes, let me say that, let me just make this with the black one. And we know ai vector dot bj vector, it is given by, that gives 2 pi times del of ij, which gives basically, this is the canonical delta. So it is 2 pi for I equals to j and is equals to 0 for I not equals to j. Alright, so we have to use this. Okay, so this is the information that we already know. Okay, right? This is the stuff that we know from our lectures. Now let's do the parts. So for part A, let's start with the left hand side. So we have to prove something. So what we do, we're going to do this that you must have done in your school as well. LHS equals to RHS. So the LHS is B1 vector dot B2 vector cross B3 vector. Alright, this is the LHS, and now we have to prove that this LHS equals to RHS, and the hint is given that we have to write B1 vector in terms of this AI vectors and then use the orthogonality relation which we have already written here. Alright, so let's do it. So B1 vector I will write as 2 pi times E2 vector cross E3 vector divided by E1 vector dot E2 vector cross E3 vector, and we have to take a dot product B2 vector cross B3 vector. Alright, now so here we are seeing this kind of vectors. To do this, we need to know one identity. So this identity we need to know. So this problem we need one more identity which is not given in the question. It is A vector plus B vector dot C vector cross D vector, that is given by A vector dot C vector times B vector dot D vector minus A vector dot D vector times E vector dot C vector. Okay, so we are going to use this identity. Now using this identity, continuing with our problem, what we can write is 2 pi divided by, I will have this value E1 vector dot E2 vector cross E3 vector here, and this cross, and what else we have is we have E2 vector cross E3 vector dot B2 vector cross B3 vector. Alright, so now we are going to use this identity, the cross product identity that we have, dot product of these two cross products. So from here what we have 2 pi A1 vector dot E2 vector cross E3 vector, and this I can write it as E2 vector dot B2 vector times E3 vector dot E3 vector minus E2 vector dot B3 vector times E3 vector dot B2 vector. Right? So this is what we are going to have. Now using the orthogonality condition, we know that okay, this is going to be 2 pi, this is going to be 2 pi, this is going to be 0, and this is also going to be 0. So from here what we will have 2 pi divided by E1 vector dot E2 vector cross E3 vector times 2 pi whole square, or simply I can write it as 2 pi whole cube, this E1 vector dot E2 vector cross E3 vector, which is our RHS. If we check, this is the RHS that we have 2 pi cube on this. This is our RHS. So LHS, or let me just write therefore we have proved is that LHS equals to RHS and hence proved. Okay, so we have to prove in this form, and we have proved it. Now let's go to the B part. B part, again we have to prove something. So what we have to prove is that this identity 2 pi times B2 vector plus B3 vector divided by B1 vecter dot this will be equals to A1 vector, and etc. as well. So we have to prove it for the other vectors as well. So because of time constraint also, I will also just prove this identity, and you can just prove it for, like, instead of B2 vector B3 vector on the top, you can numerator you can take B1 vector B2 vector B1 vector B3 vector and so on. Alright, so we will prove this. Okay, and alright, so let us do this question, this part B, and let's start with part B from here. Right, okay, so we will start with the left hand side LHS. So LHS is given to us as 2 pi times b2 vector cross b3 vector divided by b1 vector dot b2 vector cross b3 vector. Okay, and if you look closely, look at that, like this is this is the same thing. So like if I write b1 vector, I write it at 2 pi times e2 vector cross e3 vector divided by a1 vector dot e2 vector cross e3 vector. Now instead of this ai vectors, you just replace it with the bi vectors, and that is what we have done here. Instead of a2 we have a b2, instead of e3 we have a b3. So basically you can see that what we are doing is we are making a reciprocal lattice vector from a reciprocal lattice vector itself. Okay, so this is going to give us this a very interesting proof. Okay, so this is what we have to prove. Suppose primitive vectors are constructed from bi vector in the same. Suppose primitive vectors are constructed from the bi vector in the same manner as the bi are constructed from the ai vector. So basically, we have to prove that this kind of thing. So prove that these vectors are just ai themselves. Okay, so what we are doing is we are making the reciprocal vectors from the reciprocal vectors, and we have to prove that they are going to be the Bravais lattice vector itself. We are making these new bi vectors from this bi vectors, and we have to prove that they are going to be the ai vectors, in short. Alright, so now what we will do is we will keep this b2, this will be a b2 vector plus b3 vector here. I will do a b2 vector, and then I will write this b3 vector in form of this ai vectors. That will be 2 pi times a1 vector cross e2 vector divided by a1 vector dot e2 vector cross e3 vector. Alright, now from here what we will have, so we are left with 2. I will take this 2 pi outside because this is just a scalar quantity, and then this dot product, that is also scalar. So I will have 2 pi whole square b1 vector dot b2 vector cross b3 vector. Okay, this is one scalar, and then we have a1 vector dot e2 vector cross e3 vector. This is our another scalar. Right, and other than that, what I have is I have b2 vector cross a1 vector cross e2 vector. Now to solve this triple cross product, we again need to know an identity, and this identity this time is given in the question as well. So identity that we are going to use is a vector cross b vector cross c vector, that is given as b vector times a vector dot c vector minus c vector times a vector dot b vector. Alright, so now here instead of a vector, what we have, instead of a vector we have our b2, instead of b we have our a1, and instead of c we have a2. So now we will just use this formula for this cross product. So what going back to our problem. Now what we have this scalars. Okay, now let me just write it. So now let me just make b1 vector dot b2 vector cross b3 vector and a1 vector dot a2 vector cross e3 vector. Right, and this cross product, now this will be written as a1 vector times b2 vector dot a2 vector minus a2 vector times b2 vector dot a1 vector. Okay, now from the orthonormality condition, b2 vector dot e2 vector, this will give a 2 pi, and b2 vector dot a1 vector, that will be 0. So what we are left with, we have a 2 pi whole cube. Alright, and I will have the same b1 vector dot b2 vector cross b3 vector, and I will have this a1 vector dot a2 vector cross e3 vector, okay, and times we will have an even vector actually. Okay, from this cross product that we have is 2 pi times of even vector, and this second term will be 0. So 2 pi I have taken here, and this even vector. Now this b1 vector dot b2 vector cross b3 vector, you can see that it is given in the a part as well that we have proved. This b vector dot b2 vector cross b3 vector, that will be equals to 2 pi whole cube divided by this a vector dot e2 vector cross e3 vector. So so I can just write it here. So this will be now using the result, of part A, what we can write it as, we can write 2 pi whole cube, this will be written as 2 pi whole cube, and I will have on the top I will have a1 vector dot a2 vector cross a3 vector, and this is coming from this one. Okay, this is coming by replacing this from part A. Alright, and this will be this a1 vector dot a2 vector cross a3 vector. Okay, so this is what we have, and we have an even vector. So now 2 pi cube we cancel out, this 2's we cancel out. So what we are getting, we are just getting even vector, and that is equals to our right hand side. So again what we have, therefore we have again proved that left hand side is equals to right hand side, and proved. So basically what we have proved here is, so we have proved that the reciprocal lattice of the reciprocal lattice is the original lattice. Right? So we have proved here, if you take the reciprocal lattice of the reciprocal lattice, then you will get back your original lattice. Okay, and here you can as given, you can check it for other e2 and e3 vector as well. So instead of taking b2 vector b3 vector cross product, you can like basically you can try out this 2 pi times, you can make b1 vector cross b2 vector divided by b1 vector dot b2 vector cross b3 vector, and you can check that this thing will come as a3 vector. Okay, similar to the b3 vector. Okay? Similar to b3 vector is e1 vector cross e2 vector, so we will get a e3 vector. Okay, so this kind of things you can do on your own. So let me just draw. Okay, so these two things, do it yourself. Okay, DIY. So you can do it yourself. Okay, one thing will be that so we have taken the e2 vector. So what we can get is the 2 pi times b3 vector cross b1 vector divided by b1 vector dot b2 vector cross e3 vector. That will come as your e2 vector. Okay, similar to your b2 vector. Right, b2 vector is e3 cross a1. And another thing that you can prove is that 2 pi times b1 vector cross b2 vector divided by b1 vector dot this b2 vector cross b3 vector, that is given as e3 vector, similar to your b3 vector. How you define the b3 vector? 2 pi times e1 vector cross e2 vector divided by that. Right, so you can try it out, and you can do it. Okay, or you can just replace the values 1 2 3, and you can see that this will come. Alright, so we are done with part B. So let's go to part C then. Okay, so what we have in part C? In part C, what we have to do, we have to again prove something. We have to prove that the volume of a Bravais primitive primitive cell is given by this, and using the result of part A, we can thus prove that the volume of the reciprocal lattice vector will be just 2 pi cube time divided by the volume of this Bravais lattice primitive cell. Right, so Let's do this part C. Now consider a general parallel pipe this is with edges A vector, B vector and C vector. Alright, so what I'm saying is that, okay, so let's say you have your A vector, B, you have your x cap, y cap and z cap like this. You have x, your y and this is your z. Let's say you have your this parallelepiped. This is A vector here. Let's say your B vector is in along this direction, along the minus phi cap, right? I'm just taking along the minus phi cap, and let's say this is your C cap direction is also in some this direction, C vector. Okay, so this you can check that this will form a parallel pipe. Okay, this is basically a parallelogram in 3D, right? So hopefully you will be able to see this. Okay, this parallel you can meet, and this will be a s vector, which I will explain what is this s vector. Okay, let me just meet this x vector with some the red line. Okay, so this will be your s vector, which is basically the cross product of your A vector cross B vector. Okay, so it will be perpendicular to the A vector cross B vector line, and A vector cross B vector basically gives you the area of this, or the base of this parallel pipe with a 3D parallelogram. See, okay, now the area of its base parallelogram spanned by vectors A vector and B vector is A is given by mod of A vector mod of B vector times sin theta, which is basically A vector cross B vector, or we can write this as which is equals to mod of A vector cross B vector, where theta is the angle between A vector and B vector. Now note that S vector, which is basically A vector cross B vector, is perpendicular to this base the height corresponding to the base corresponding to this base is then this height h will be equals to mod of C vector dot S vector by mod of S vector, which is just the projection of C vector onto the direction of S vector. Therefore the S vector, therefore the volume of the parallel pipe fight is V is equals to A times of H, that will be is equals to mod of C vector. So I have read E. What is A? A is your mod of A vector cross B vector basically, and this H as written will be equals to C vector dot S vector. So C vector dot S vector, and S vector is basically your A vector cross B vector divided by mod of A vector cross B vector. Right? We just go from next 20 minutes on the gap. And this, if you just cancel out stuff, okay, so this two will just get cancelled out. Alright, so what we are left with will be C vector dot A vector cross B vector. Okay, so this will be the volume. Volume will be given by C vector dot A vector cross B vector. So this is what we had to prove. Okay, so like if there are I have written it as A1, A2, ABC. Instead of this, we can write it as A1, A2, A3. Okay, so let okay, and I have taken say that A vector is equals to A1 vector, B vector is equals to E2 vector, and C vector is equals to E3 vector. Then volume V is equals to E3 vector dot A1 vector cross E2 vector. Okay, I guess this is you can I hope you understand that A1 vector dot A2 vector cross E3 vector is same as E3 vector dot A1 vector cross A2 vector. Okay, so that is the same thing. Okay, that is the cyclic thing, or I can write this as A1 vector dot A2 vector cross A3 vector as well. Right, so this is what we have proved here. It is proved. Now thus the volume of a Bravais lattice primitive cell spanned by primitive vectors AI vector is V equals to mod of A1 vector dot A2 vector cross A3 vector. Now moreover, from part A, right, the volume of, okay, if that is the volume for this thing, Bravais lattice, then B1 vector dot B2 vector plus B3 vector mod modulus value will be the volume of the reciprocal lattice vector. Alright, okay, the volume of the reciprocal lattice primitive cell, which is given by B1 modulus of B1 vector dot B2 vector plus B3 vector, is then 2 pi whole cube divided by this capital V. Okay, which is the volume of the R. Okay, so basically what I am saying, what we have achieved is this: volume of the reciprocal lattice is equals to 2 pi whole cube volume of the Bravais lattice, where this is the volume of reciprocal of the reciprocal lattice, and this is the volume of Bravais, volume of the reciprocal lattice primitive cell. It is for the Bravais lattice primitive cell, right? So this is what we have proved here. V of the rectangle is equals to 2 pi times of the Bravais lattice, right? Okay, let's go to problem number 4 quickly, and I guess this is the last problem of this session because we are already near the end of the session time. Alright, so problem number 4. So this is problem 2 from chapter 2 of Introduction to Solid State Physics by Charles Kittel. Alright, so in this problem what we have to do is, this is a very interesting problem. So what we have to do is, so what we have given is that for a hexagonal space lattice, the primitive transition vectors of the hexagonal space lattice, they are given to us. We have to show that the volume of the primitive cell is this. So now we have already shown in the previous then how we define the cell volume. So the cell volume, we already know this will be given by E1 vector dot E2 vector cross E3 vector. We just proved it in the previous question. And here this E1 vector, E2 vector, what are our here? Our E1 vector is equals to root 3 A by 2 x cap plus A by 2 y cap. E2 vector is equals to minus root 3 A by 2 x cap plus A by 2 y cap, and E3 vector is equals to C times of Z cap. Alright, this is given to us, so we will just put them in this, we will just put A1, A2, A3 in this formula. So that, so our volume, cell volume will be given by E1 vector, which is root 3 A by 2 x cap plus A by 2 y cap. Okay, dot product E2 vector minus root 3 A by 2. I should have written that in blue maybe. Okay, that's fine I guess now. Let me just write this in. Sorry about that. This is the given definition, so we should write it in different color. So like it is given that here, given that E1 vector is equals to root 3 A by 2 x cap plus A by 2 y cap. A2 vector is equals to minus root 3 A by 2 x cap plus A by 2 y cap, and E3 vector is equals to C times of Z cap. Alright, and this is what we are already given, and we are just putting these things in this formula. Now E2 vector is minus root 3 A by 2 x cap plus A by 2 y cap, okay, this E2 vector cross E3 vector, which is C times of Z cap. Okay, so this is what we have to solve. So whenever you have to solve this kind of problems, we need to remember that. Okay, so let's say just a small note. We should remember that x cap dot y cap will be equals to y cap dot z cap will be equals to x cap dot c cap will be equals to 0. So the dot product of x, y, because they are orthogonal, so these will be 0. While x cap dot x cap equals to y cap dot y cap equals to z cap dot z cap is equals to 1. Okay, because they are orthonormal to each other. These are basic things, but they will really help us if we just write them here and we do this kind of like complicated problem when we have some cross products and then we have this dot product. We can solve it by doing a determinant method as well, I guess, but just writing it out would be also easy. If you know x cap cross y cap will give you z cap, then y cap cross z cap will give you x cap, and similarly x cap over y cap will give you z cap. Then y cap cross x cap, if you have instead of x cap y cap, then that will give you a minus of z cap. So this is the property of the cross products. Alright, and if you we will have y cap cross z cap x cap, and thus we will have z cap cross y cap is equals to minus of x cap, minus of x cap, and then we have z cap cross x cap is equals to y cap, and okay, and then we will have x cap plus z cap will be equals to minus y cap. Okay, so we need to remember these identities, and these are very easy. I guess you might already know. So now what we are going to do, so to solve this problem, what we are going to do, we are going to solve this p vector, which is basically our e2 vector cross e3 vector. Okay, so first we are going to solve this e2 vector cross e3 vector separately. So our p vector, which is equals to basically e2 vector cross e3 vector, so that is given by this minus root 3a by 2 x cap plus a by 2 y cap. I have to take a cross product with c times of z cap. So what we get is, we get minus root 3 ac by 2, which is a scalar, x cap cross z cap, and plus ac by 2 y cap cross z cap. Alright, and now from the above table we know x cap cross z cap will be a minus y cap. So we get root 3 ac by 2 y cap, minus minus we get plus, and y cap cross z cap, here you can see y cap cross z cap is an x cap, so it is, just move it, y cap cross z cap is x cap, so we will have an ac by 2 x cap. So this is our a2 cross a3 vector. So using this what we can get, our v will be is equals to our e1 vector, which is root 3a by 2 x cap. We have root 3a by 2 x cap plus a by 2 y cap, and we will take a dot product now with this e2, this p vector, which is e2 vector plus e3 vector, which we have found as root 3 ac by 2 y cap plus ac by 2, or let me just write it as ac by 2 x cap plus root 3 ac by 2 y cap. Alright, now if I do a dot product, so if you do a dot product, what you get is root 3 a square c by 4. Okay, these two scalars with x cap dot x cap plus we will have a 3 a square c by 4. So I am just showing you, instead of writing directly the answer, I am just showing you this time how this calculation is done. X cap dot y cap plus we have a square. Okay, from these two, and we do x cap the first term and the second term of the dot product. Then we have a square c by 4, doing this and this, a square c by 4 y cap dot x cap plus we will have root 3, using this, doing dot product of this and this, root 3 a square c, root 3 a square c by 4 y cap dot y cap. Okay, now from the also non-numericality condition, which we have written above as well, x cap dot x, these are 0, these are 1. So what we will have, x cap, this will give us 1, this will give us 0, this will give us 0, and this will give us 1. Alright, so our volume V will be written as root 3 a square c by 4 plus root 3 a square c by 4. So overall we have a volume equals to root 3 a square c by 2. So this is the volume of our primitive unit cell of a hexagonal space, that is. Okay, now the B part is show that the primitive translations of the reciprocal lattice are this. Now we have to show that the lattice is its own reciprocal but with a rotation of axis. Okay, so now we have to show that this b1, b2, b3 vector are given by this. So we just need to calculate this b1, b2, b3 vector. So for part B, now I will just calculate so because of the lack of time, I will just calculate b1 vector, and similarly you can calculate the b2 and b3 vector as well. So calculate b1 vector, we will just use a formula which is b1 vector is equal to 2 pi times e2 vector cross e3 vector divided by a1 vector dot e2 vector cross e3 vector. Alright, so now e2 vector cross e3 vector we have already found from the previous one. So let me just find this a1 vector dot and this also we just found. So we have just found both of these two things from the previous equation. We have this e2 plus e3, and what we calculated is the volume V. It was a1 vector dot e2 vector cross e3 vector. Okay, so we have both these two values. So we will just put these values here. Now e2 vector cross e3 vector is root 3 ac by 2 x cap. Okay, from part A. Let me just write it as from part A. From part A, we know a2 vector cross e3 vector and a1 vector dot a2 vector cross a3 vector. So our b1 vector will be equals to 2 pi times, instead of a2 vector cross a3 vector we will write ec by 2 x cap plus root 3 ac by 2 y cap divided by this is just the volume, which is root 3 a square. Okay, root 3 a square c by 2. Alright, and if we do this, what we get our b1 vector is equals to, we just divided, we say ac by 2 is right, it will be 2 pi divided by root 3 times of a x cap plus 2 pi by a y cap. Okay, so and this is what we have to show as well. This is 2 pi by root 3 x cap plus 2 pi by y cap. And similarly you can find b2 and b3 as well. So this is DIY. You can do it yourself in the similar fashion. But you will get 2 pi is equals to minus 2 pi by root 3a x cap plus 2 pi by a y cap, and b3 vector will come as 2 pi by c z cap. Okay, so that is the same manner. We just have to put the this ai vectors in the formula, and we can calculate b2 vector and b3 vector as well. Now we have to show that the reciprocal lattice vector for this hexagonal one, that is also similar, that is also so that a reciprocal is its own lattice is its own reciprocal but with a rotation of axis. This is we have to prove. So that is the reciprocal one is also a hexagonal lattice. This we have to prove. Now here e3 vector and b3 vector are both along z-axis and in the xy plane the lattice and the reciprocal lattice are as shown below. So okay, so we can make our lattice and reciprocal lattice. This you can check. Okay, so like if you have an O vector and if you make this A1 and A2 along the x and y direction, so this is your x and y, then if you start with this O point, then what the A1 and A2 vector that we have, so I will have one A1 vector here. Because of this A1 vector I will have one point here, I will have one point here, and I will have another point here, I will have another point here, I will have another point here, and I will have another point here. So this will be the xy plane of our reciprocal lattice vector. So this you can check. The diagram is not that clear, but you can check it that if you make it, this will be this this you will get from your A1 vector, okay, which is as you can see, this will be some root 3 a by 2 x cap plus a by 2 y cap, and then from minus root 3 a by 2 x cap, a by 2 y cap, and c times z cap. That will be c times z cap will be in some other direction, right? So one will be this A1 vector, then this will be, this you can get with your A2 vector, and this will be some and then the other points will be just in this plane. The other points will be just by linear combination of this A1 vector, A2 vector, you can form this thing. Okay, so this is your so this will be our xy, this will be the xy plane of hexagonal lattice. Alright, and then if we form the reciprocal lattice vector using the bi vectors, so if we form them and we start with this this point, so similar to this we will have some points here, but you can check that this will be little rotated. Now we will again have an hexagon, but this hexagon will be a little rotated. I'm just drawing a very rough diagram right now. I'm just joining them here. So this will also be a hexagon but a little rotated, and this you can check, this will be your b1 vector, alright, and this will be given by your b2 vector, alright. So this will be the xy plane of the reciprocal lattice from hexagonal lattice. Okay, so by looking at about figures, by looking at above figure, obviously the reciprocal lattice is also a hexagonal lattice, but with a rotation about z-axis by an angle of 30 degree. Okay, and this angle is basically the you can by, as you can see, this a1 a2. So this within the xy plane, because a3 and b3 they are along the z-axis, the only rotation you can see about the z-axis, so that you can see the angle between a1 vector and e2 vector is the you can say the angle between a1 vector and b1 vector. Okay, so that will give you this rotation angle 30 degrees. So this you can find out yourself. Alright, so now we are already actually out of time. So the C part we will solve in the next session, the C part of this problem, where we have to find the first brilliant zone of this hexagonal space lattice. So that's a small part, but we are already quite out of time. So we will do it in the next session. I will start from this problem number 4 itself, from part C. Right, I'm just stop sharing now. Right. Okay, so we are at the end of this session. So in this session we have solved some problems regarding the Bravais lattice and the reciprocal lattice, and we have also seen the problem with the Wigner cell. Unfortunately, because of limited time, we could not solve the last problem completely, which involves the where we have to find the brilliant zone for the hexagonal lattice. So, so I will start the next session from part C of problem number 4, and then we will also do one more problem within this similar problem number 5, which was also not done, which is within this similar hexagonal lattice and its reciprocal lattice. All right. Thank you for your attention.